Right, okay, we're sticking to quite a tight time frame. We're going to be here until around 7:15, so I don't want to just hang around too long, so I will get started whilst people do continue to arrive. So thank you for joining us for this evening's webinar. My name is Tim Sainty and I'm the Membership Director at the Chartered Institute of Plumbing and Heating Engineering. Before I introduce our speakers, I would like to thank HVP magazine for their support for tonight. And with over 400 registrations received, this must mean that we have either an interesting topic or a successful marketing plan, so it's great to see you here. Our speakers have got some occasional poll questions included, so they will ask questions back to you, so please do take the opportunity to give a response to us. No right or wrong answers or identifying people for the answers that they give. It's just to sort of get a temperature check from the room, so please do get involved. I've already mentioned we've got Q&A feature included, and we've allowed for a good half an hour hopefully for questions and answers to go ahead, so do include those in here. Again, I've mentioned we've recorded this and we'll be sharing it afterwards. So on to our speakers and panel. And from the CIPHE technical team, I've got Paul Harmer and Jerry Whiteley. And then from two of our industrial associate support members, I'm pleased to welcome Lewis Bergman from Sunam and Stuart Dogwell from Fabdeck. So now the first speaker this evening will be Paul Harmer. I know him well enough by now. So I will pass over to Paul and he can get started. So thank you.
Thank you, Tim, and welcome everyone tonight. I'm just going to start sharing my screen, Tim. And will you just confirm once it's on the screen that you can see it?
Yes, just need to go to present to view.
Yeah, okay.
Perfect.
Right. So welcome everyone. Yeah, my name is Paul Harmer. I'm lead technical consultant at the Chartered Institute of Plumbing and Heating, and this evening, you know, we're going to be discussing some really interesting points, some really critical technical points as we transition towards net zero, especially around low temperature and the effect on domestic hot water systems. Before I start, I just wanted Tim's going to put a question up, a poll, and it'd be interesting for everyone to vote or not vote or to answer the question. So Tim, is it okay if you just put that on before we start? So the question is, which would be the order of priorities to consider in the delivery of hot water? Of importance from left to right, being the most important. We know they're all important, but what would you class as 1, 2 and 3?
I'll let this run for around 30 seconds. Just let people read through the different responses. Okay, so I'll give that a few more seconds now. Thank you, everybody. I will end that poll now and I will show you the results.
Okay, interesting. So, as I can see, there's quite a few people that have put efficiency before comfort. Clearly, safety is the main one. That's an interesting set of response. So I'll move forward, Tim, in my presentation. So do you want to turn it off? Okay. Right. So this is the order I've put it in, and we can argue about it as long as we want later on and debate it. But clearly, obviously, safety is number one. The safety and health and welfare of the public is what the CIPHE is all about through professional plumbing and heating systems. There is an argument, and I know you can actually get comfort and efficiency all in one. We know that, but obviously, if a consumer had a choice and they're looking at a heating and hot water system, they're going to want to be comfortable. It's critical. Safety, obviously, then comfort, efficiency as number 3, and we can argue and debate that later on. So one of the first things as a plumbing and heating installer, a public health engineer, you know, we all talk about keeping it hot, keeping it cold, keep it clean, keep it moving. Those 4 key things, and this is a graphic developed by one of our members of our technical working group for safe water, which is David Harper, who's an expert in Legionella. He's been working all around the world around Legionella. He emphasises this this graphic every time when he presents. It's really important. So before we start looking at efficiency and what the consumer wants, it's just key to have a look at the key safety regime. So we need to be storing hot water between 60 and 65. We need to be distributing it no lower than 60. We need it to be between 50 and 60 at the outlets. And if we have a hot water return, it has to be greater than 50 degrees on the return. There's 2 sort of conflicting guidance out there. The health and safety guidance, HSD 274, which asks for that temperature 50 to 60 to be reached at the outlets within 1 minute, whereas the water regulations say 30 seconds. Clearly, obviously, cold water we need to keep below 20 degrees. So moving on, pasteurisation and protecting against Legionella. Our water safety group, again, especially when we're talking about low temperature heating systems, and when we're looking at heat pumps, for example, you're probably looking at 65 degrees maximum flow temperature, albeit the innovation is moving towards higher temperatures, such as 70 degrees. It's not great because of efficiency, but if we're storing at 60 and our flow temperature coming into that source, that hot water system should be at least 5 degrees greater to be able to get that heat transfer. Above 60, we're looking at 2 minutes exposure to kill off Legionella. So again, if we're looking at low temperature heating systems, our working group would want to see pasteurisation every day. And again, when do you pasteurize? If we pasteurize in the evening, and that's a good debate for today, if we pasteurize at say 3 in the morning, water's not moving. If we pasteurize in the day, water's moving, and that's what we need. So for example, the distribution system, hot and cold water, we need that pasteurizing to be happening in the pipework as well, but be interesting to hear views on that. The different type of hot water systems, I've focused on about 5 here, but the key one I'm looking at today is your traditional indirect cylinder. We will be touching on thermal batteries, which is on the right hand side there, which Sunamp, one of our industrial associates, will present. But I'm just going to show really the 2 main systems, system type C and D. System type C is an indirect hot water system with a coil inside, and system type D with an external plate heat exchanger. There's a misconception out there that, you know, we've got low temperature, we're running a heat pump, that we need to have a coil which is a larger surface area. That is correct, 100%. But what we see is the coils that are spread out through the whole cylinder, you get that degradation effect of the heat transfer of the coil. So you want that coil, the lowest part in the coldest part, to maximize heat transfer. So as you can see, 2 basic examples there. As it's charging, the one on the left, as soon as it reaches the coil, it drops off. But it's straight away, the hot water is crossing over the coil straight away, which means it's dropping off even more. So that affects the recharge rate, time, and heat transfer. The other thing to bear in mind in a hot water system is to make sure that the primary system feeding that coil is sufficiently sized. So if we're heating with a heat pump, low temperature, we may have higher flow rates. So every component, every pipe within there will have to be sized sufficiently to deliver the flow rate required to that coil. In addition to that, the coil itself, if we were just to pick up a standard cylinder from standard coil off the shelf, rather than actually getting something that's ready for a heat pump, or it can be is sold for those higher flow rates, then we can get significant pressure drop. So we may see the actual performance of the recharging of the cylinder and the amount of available hot water drop off considerably, purely because the primaries are not sized correctly. Just at this point now, Tim, we've got another poll, and I mean, the example on the screen here, I've just done a basic calculation, which is just a complete rule of thumb. It's mentioned, I believe, in the MCS standard. It's just to get an understanding of how much hot water you would use in the day. So, Tim, do you mind just bringing up that question? I'll be interested to see how installers and designers are getting to that number before they size a cylinder. How are they calculating it? So what method do you use for sizing the hot water cylinder? So there's some examples there. So that should say patterns, by the way, customer engagement and usage patterns, the first one. That means understanding the customer's exact needs. We have manufacturers' calculations. So calculators could be online. You might want to size it based on the number of bedrooms, the number of bathrooms, the number of occupants, or you might do all of them.
Okay, as before, I'll leave that for about another 10 seconds, Paul.
No problem.
Okay, so that's slowed down now, so I shall end the poll and share the results.
All of the above. Interesting. Number of occupants, number of bedrooms. Okay, so the basic example on there is industry likes to bat around the number 45 litres per person per day. And I know MCS use something similar. And what industry says is if it's a number of bedrooms plus 1, times that litres per day will give you the daily water usage. However, you may have more occupants in there than bedrooms. There might be 6 in there, so you will go with the number of people. But again, this is all just a rule of thumb. The other thing here is daily hot water usage here. That's what we're talking about. As we all know, that could be split into different parts of the day as a normal hot water pattern. So again, it is a very rudimentary rule of thumb. And it has worked very well for high temperature, high output heat generators, such as a boiler. But now we move towards lower output, low temperature systems. We've got to be a lot more careful when we actually size that cylinder volume. So I'll just move to the next slide. Part of the Institute's work recently with the low temperature heat and hot water course, we've been doing a lot of work on tools, and we've done a lot of research, and we've taken a step back. Rather than creating, to start with, a tool where you put your number in and you get a number out, it's like a black box effect. We've tried to bring it back to the old days with a good old nomograph, where you can actually, for education, see, as you move things up and down, left to right, the effects. We've created a lot of this stuff, and it will come forward as part of the new low carbon training course, but this is just a snippet. As you can see there, bottom right, you've got maximum heat generator temperature 65, maximum cylinder temperature 60, usable hot water of 40. And the key thing here is the heat generator is operating continuously during the cylinder draw off. There's so many different parameters in hot water systems and we can't cover them all. So this is just a pure example. But as you can see on the left, I've plotted a 6 kilowatt heat generator, and it will give you the cylinder size with a draw off of 225. So you can see there, it's just above 300 litres. If I just split that down now and say, actually, we'll use 130 out of those 225 in the morning, and we'll use 95 later on in the day, then we have that period of reheat. So as you can see, if I'm only using 130, then my volume, as long as I've got enough reheat time within that period of use, then I'm able to reduce that cylinder size. This is for an indirect cylinder. This is all from BS 12831 2017 part 3. This is different for the external plate type system, because you're able to recharge the whole cylinder and you do not get that degradation effect within the cylinder of the coil. So again, my point here is, and we're not here to answer the question, it takes a bit more thought, but understanding the consumer's needs and requirements can actually influence what you are sizing. If you undersize a cylinder, if we go back to water safety, and this is the critical bit, if you undersize a cylinder, undersize a coil or heat exchanger, then those temperatures within the pipework, within the cylinder, will be hovering around for longer at those temperatures where Legionella can grow, which increase the risk to the consumer. And that's why I always emphasize safety first. It's not just about efficiency, which is very important, because as we move towards net zero, it's about safety. Safety is number one. So while we design for efficiency, we just cannot forget safety. And we've all been there. I've been there. You become focused on efficiency. It's so easy as an engineer to just miss that safety element. So again, there's more to just sizing a cylinder than what we used to do. And it's getting the installers to understand this as we transition, that we can't use those old methods. We've got to embed more knowledge now to enable the consumer to be safe and for them to be comfortable. I know the new guidance has come out, so there's a new domestic heating design guide, which we were originally part of. Unfortunately, there's a statement in there that says this is not to be used for sizing hot water systems for flow temperatures lower than 70 degrees. So you should seek further guidance. Well, the good news is the CIPH has been working on that guidance, and we're trying to create some tools which will help the installer. Simple nomographs like this where you can use it. But the key thing here is always consult the manufacturer. The manufacturer product will be specific, and you will need advice from them to see whether it's fit for purpose for your application. This is only guidance. So yeah, so that's me finished, Tim. Thank you very much for everyone's time. And I will stop sharing my screen, Tim.
Sorry, I was on mute first time today. Thank you for that, Paul. Some questions have already come in, but if people are okay with that, I'm going to save them until we get into a wider discussion at the end. They will be picked up, but now I would like to introduce Jerry, who will shortly share his screen and give a short presentation to follow up on the one from Paul. Over to you, Jerry.
Okay, thanks, Tim. I think we're on screen now, are we, with the slides?
You are, yes.
Thank you. Apologies to everybody, I can't get it to full screen. I think it's I'll have to go with what we've got, if you don't mind. So what I want to introduce is something that sort of tends to come around quite often through the technical helpline, where issues arise, which is why we're there for the technical helpline, and just to sort of go over some probably some old ground for some people, but clearly for the fact it comes through the technical helpline. A lot of people don't really understand the different grades of cylinders and things like that. So in this first slide, here we're looking at standard copper cylinders, a standard indirect there on the image, and they come in 3 grades, grades 1, 2, and 3. Now, that being the different thicknesses of copper, and that ranges from 0.7 mil to 2 millimeters. It differs slightly from one manufacturer to another, but fundamentally the difference in the grades is to do with the head of pressure behind it, and that's why they're made in those different grades. Now, at the same time, we've also got to factor in the pH value of the water, and the pH value of the water is something that comes up time and time again through failure to do so, actually, from the installer's perspective, where we can receive calls coming in to say, what's gone on with cylinders? They're not being made as good as they used to be. What's going on with them? And then when you start asking the questions about, did you test the water, the suitability for that cylinder? And then you get the answer back, well, no, I didn't know you had to, or something like that. then clearly you can start to see that things go wrong very quickly. So my first question I've got there, Tim, I think, is it on this on this slide, isn't it? If we can put that one up to the audience.
Yep, hang on a second.
Okay.
You should see that on screen now.
There we go. So it's what's the most important material for an atmospheric hot water cylinder in a soft water area? Over to you.
Okay, I've still got answers coming in, but I'm going to give it about another 10 seconds.
Okay.
Thank you, everybody. I'll draw that to a close now and share the results on screen.
Okay. There we go. Yeah, it's clearly is correct at the bottom, the stainless steel versions. And if I'm honest, I do find that some installers don't realise that you can actually get a standard indirect cylinder that traditionally we've all fitted for donkey's years in copper. They actually do exactly the same one in stainless steel. And generally speaking, you get a longer warranty with a stainless steel cylinder. Again, in some manufacturers, they're not necessarily of a thicker material, but they tend to last longer in soft water areas. Let's see if I can get this to go down to the next slide. So what we've got to consider then is when we come to install a cylinder, that it's what checks have we made with regards to, obviously we're going to look at pressure and things like that. But if we actually look at the details of the manufacturer's terms and conditions, this will also highlight as to why we need to do certain things, certain aspects, and in particular around testing the water in the first place. In actual fact, I'll blow the trumpet a little bit for Fernox. Fernox, for instance, have a section on their website where you can put the postcode in for the area you're working in, and it will pop up and give you the water quality for that area. And thereafter, you can find solutions based upon what answers you get back. So I do find the Fernox website very good for that. But what we've got to look into is things like if the cylinder fails, and you're in that situation where maybe it's only been fitted for a couple of years, of course you're going to scratch your head and go, well, hold on a minute, surely these last longer. I used to fit these in the last 25, 30 years. Not all of them, because of clearly, if we end up with a situation where the water is eating away at the copper, then they can go very quickly. And we had one gentleman phone up who'd come across, let's say, many copper cylinders on a housing estate, and they all failed within 2 years. So clearly there's something went wrong there. So it's about what action you take. And as it says within terms and conditions, manufacturers like to know what's happening before you take any remedial action. They also like to state that the unit can only be installed on potable water, mains water, not on private water, on the well water, things like that, spring water. Not all the manufacturers. There are some of the manufacturers that make them specifically that will do both, if that's the way to say it. But not every one of them. Once you read the terms and conditions, they're not suitable copper cylinders for well water. So when we look at defects caused by corrosion or scale deposits, it says in most places I've read, they're not covered anyway from that perspective. So in real terms, yes, you get a 10-year warranty on a copper cylinder, potentially a 12-year warranty on a stainless steel cylinder. But ultimately, if you haven't followed those details of the terms and conditions, you don't get any warranty at the end of the day. So it's down to the installer to do that survey and make sure that they're checking things over before they just go out and buy anything off the shelf, really, in real terms. So I've got another question on this one, Tim. The next one.
One moment.
Thank you. So the next part of that terms and conditions comes under this, obviously the servicing, etc. of cylinders. So there's the question. Do you carry out regular servicing of a customer's hot water cylinder? over to you.
Okay, same again, 10 more seconds.
Okay.
And there you go.
There you go. Yeah. What I tend to find, again, going back to the hotline, is that you tend to find that in reality, there's not much of it. We all know it's annually as an answer, but generally speaking, we tend to find it's sporadic is maybe the best word to use. Not everybody's doing it. Other people are too busy doing other types of work or whatever it might be. But if you go around asking the consumer when was the last time you had your unvented cylinder serviced, you'll probably find there's not many people even knew they had to have it serviced, if I'm totally honest. So it just depends a little bit. It's mixed. I'll say it's a very mixed picture when it comes to servicing. So again, when it comes to things like depicting whether or not we therefore have any warranty cover, here we have a stainless steel unvented cylinder carrying a 25-year warranty on it. But generally speaking, again, if the installer's not carrying out the set procedures and the guidelines from the manufacturer, it's not worth the paper it's written on. So other aspects they highlight is it must not be modified. So we had a call the other day for a guy saying he wants to put a plate heat exchanger in. Unless you contact the manufacturer before you do that, that cylinder might have no warranty. So you need to know, you've got to check if there's any terms and conditions there about modifications, you know, check with the manufacturer. As it says there, potable water only. Is your benchmark document completed? Is it registered? Has it an annual service by a competent person? And as we know, there's lots and lots of incompetent persons out there, if that's the word to use, not registered, or shall we say, that fit these in all the time. So there's a lot of work goes on, is what we're saying. And sadly, we see a lot of it coming through the technical outline where it's sometimes too late. Last one there, not subject to frost damage. Well, clearly, you know, when we're doing loft conversions and things, and these cylinders get put in the loft, frost protection and disinfection, etc., for the system carried out to BS 6700. So they're all key things that come out in the small print that sometimes, basically, a lot of people are just too busy to sit down and read and get into a routine of what they do, not necessarily look into it before it's too late, when maybe a couple of years down the line it's failed and the customer's scratching their head saying, well, hang on, I spent £800, £1,000 on this. Why's that happened? Last slide is this one. So again, with installations, this has come through a couple of times as well, whereby the cylinders collapse. And the cylinders collapse whereby an installer's gone back, not necessarily to a piece of work they did, it's somebody else's work. And when you find cylinders therefore imploding, not only do you stand there and go, oh my God, what's going on here? It's some explaining to do to the consumer at the end of the day to say, why on earth this happened? And those two gadgets on either side, being the anti-vac valves to be fitted on there, goes back to the fact that you are supposed to let in, twist the TPR valve to let some air in. So when that's not occurred, of course, as the water trickles out, and I remember one guy phoned up, said he was fixing a shower in the bathroom downstairs, only to find the cylinder collapsed upstairs. And that purely was because there's no anti-vac valve on it. So these are common errors with regards to maybe, well, clearly in this case, it was wrong in the installation from day one. And then generally speaking, the installer just sort of taking it for granted that just turn the valve off and that's it. Well, actually, no, it's not. It's like anything else. It needs some air to get in there to stop that vacuum forming and atmospheric pressure crushing it. And as you see in that image in the middle, that's exactly what's happened. And it's not uncommon for that to happen in the out in the industry. Certainly, I wouldn't like to stand there and try and explain that one off to the customer because that's going to cost a lot of money. Anyway, so that really is it from me with regards to some points, some hints and tips with regards to what to sort of bring back into the table really before people to just step back and have a rethink at times with regards to what you're doing and how you're doing it. So thank you from me.
Thank you, Jerry. And if you can stop sharing your screen too. I'd now like to introduce Lucas Bergman from Sunamp. So Lucas, the floor is yours. Thank you.
Thank you, Tim. Thanks. Yeah, hi, my name is Lucas Bergman. I'm working for Sunamp, a Scottish manufacturer of heat batteries, and I'm product manager there. I just want to talk today a little bit about a new way to store energy for heating and hot water in homes, but also in commercial and industrial applications. But I'm going to focus on residential applications. So what are first of all, very briefly about Sunamp. We are a relatively small company still, but with a global ambition. We have about 50 employees, have been developing the engineering of the product since 2010, after having worked a lot of time on our materials. We have over 100 patents granted or pending worldwide, and current manufacturing capacity of 20,000 units a year, but that is growing as well. So what are heat batteries and what are phase change materials? Heat batteries use phase change materials, and these are really things that most of us, or every one of us, knows at least one phase change material. The most common and most well-known one is definitely water. Water, as you know, if its temperature drops to below 0 degrees, will freeze and solidify, and that is what's called a phase change. It changes from its liquid to its solid state. Now, that obviously is happening at a temperature where this temperature isn't very useful to us unless we want to, for example, cool down our drinks, or we want to store food or other perishable items. That's mainly what this temperature is being used for. At Sunamp, we have developed a material that is also a PCM, but instead of solidifying at 0 degrees, our material solidifies at 58 degrees centigrade. So what that means is that if you take energy out of the material, for example, by passing cold water through a heat exchanger that is in contact with the material, that water will come out on the other side at a temperature that is suitable for hot water applications in homes. And where that material is very known is in these little hand warmers. I assume that most of you may have already seen these. You usually get these at trade fairs and other occasions, and this material essentially is similar to what we use in our product, but we have worked a lot on the stability of this material. You could hardly use these for 50 times or so, whereas you can use our material for more than 40,000 cycles, which on 2 cycles a day would be equivalent to about 50 years lifespan. Now, why PCMs? The main reason for using phase change materials to store energy rather than water is that they have a significantly higher energy density, so they can store a lot more energy at the phase change temperature. So here at 58 degrees, the PCM is storing 4 times more energy than the same amount of water, or the same volume of water. What that means is that for the same amount of hot water provided to a property, we can have a storage system that is 3.5 times smaller than an equivalent unvented cylinder. In our product line, we have essentially created 4 different sizes of heat batteries. A 70 liter, 140 liter, 210 and 280 liter equivalent cylinders. And they all have the same width and depth and 4 different heights. There are direct and indirect models, essentially the same principles as in cylinders. So direct models being heated electrically, indirect models by an external heat source. But as opposed to hot water cylinders, we never store hot water. We store energy inside the PCM material. So they're all thermal stores. To give you a bit of an idea of what that looks like on the inside, this is a cut through, slightly simplified of our product. And first of all, as I mentioned, we have direct and indirect models. This is the indirect model. So we have essentially a primary and a secondary circuit, which internally are entirely separate from each other. We supply all the products with brass push fits, so that they can very easily be adapted to any install situation and location. They can essentially come out on all different sides. We have a very high-powered heat exchanger inside the PCM. And that essentially runs off mains pressure, so it provides very high quality showers. And obviously the most important part is the phase change material itself, which stores 4 times more energy than water. Also, in most of our products, we have an embedded element, which we guarantee for 10 years. And we have a user interface that essentially just shows you whether the unit is currently working or charging. As I mentioned, there's a range of systems with both the indirect and direct and indirect applications, and also, but this is only emerging, for storing energy for space heating applications as well. In particular, of interest, that part really for time shifting, which is starting to emerge as an important element for operating heat pumps in particular. These are just some pictures from installations. In this case here, what's quite interesting is you see here the footprint of a cylinder that was installed in this location previously, and this is an equivalent SunAmp unit. And on the right hand side here, you see an installation with a Daikin high temperature heat pump. So the products are suitable for heat pump applications. And to give you another idea of kind of how this can look in the field, this is a project we worked on with Gen 2 NG in Kenza. And here the challenge was to take gas out of 7 of these tower blocks, a total of 364 apartments, which were all essentially heated by combi boilers. Especially with the backdrop of the Grenfell disaster, the Gen 2, who's the project principal, wanted to get rid of the gas boilers because of the fire risk. And the solution was to create joint ground loops for all the different apartments inside the towers, and each apartment has its own small heat pump that is connected to its own electricity supply, so that there's no issues with metering, etc. And the SunAmp heat battery is providing the hot water storage in a small cupboard, which you can see at the back there and on the left. That would not have housed a normal cylinder. Yeah, and that is a very brief overview of the future of hot water storage, according to SunAmp. And anyways, thanks.
Thank you very much, Lucas. Amazingly, we are within 2 minutes of our schedule, so well done everybody, thank you for that. And it's quite handy that we are as well, because I can already see that we've got 23 questions in the Q&A, and I really did want to use this time to allow people to submit some questions, and for the panel here today to be able to do your collective best in order to be able to respond to them. I will also flag here that if we are unable to answer any questions, we will say so. We will also make a commitment to returning with an answer after the session has been concluded. So with no further ado, I will go straight into them now. And the first one that I saw come in was from Malcolm Atherton, and that was that water regs stipulate that distribution must be at a minimum of 55 degrees. Paul, anything that you would say in respect of that? And you are on mute.
Yeah, I'm now not on mute. Cheers, mate. Yeah, it's a good point. There is some nuances between HSG 274. In HSG 274, it talks about 55 degree for healthcare premises, and then 50 degrees. Obviously, the Institute and allows for the diagram we've shown a return. It should be no lower than 50 degrees on the return back to the cylinder, and we show a 60 degrees because obviously we like to see pasteurisation in the pipework. But that 55 degree will probably be a mean water between the 60 and 55. Sorry, the 60 and the 50. I touched, Paul, Tim, just because of time, I noticed there's one on scalding. Can you hear me?
I can hear you. I'm just trying to scroll through them. If you can see it, then...
Yeah, so obviously we don't allow those temperatures at the taps. They're clearly the minimum temperatures, and it needs to be blended down for obviously for scalding reasons. Those temperatures is purely up to point of use before being used for Legionella reasons. But obviously you will require some form of mixing down of the temperature, and those temperatures are in the CIPHE Legionella risk assessment book for different outlets.
Okay, thank you.
And Tim, there's just, well, because again, I can finish off on one more, and anything else, quite happily just touch base with everyone. There's one on cold water. In terms of cold water delivery at 20 degrees, what was the current thoughts for maintaining or limiting? Well, we did a bit of research, I think you remember, Tim, about 3 years ago, where we looked at heat transfer across pipework. And personally, I would say insulate all of the pipework to stop heat transfer coming across from any hot pipes, which is obvious. Again, there's an argument about, there's a lot of situations where, and I'm sure a lot of plumbers here that fitted combi boilers where they're in the airing cupboard and all the pipework runs through the hallway, or the landing, and you've got everything lined up to feed the boiler from flow all the way from hot water, cold water, all in the middle. And there's a lot of issues there with heat transfer onto the cold. So I can imagine a lot of difficulties there, and being able to insulate everything. And then the other one, which is a really good point, Tim, I'll finish off on, which a question came in, was about the effect on the whole hot water system with regards to power. So clearly the insulation of the pipework from the heat source to the cylinder, and then from the cylinder to the outlets, plays a reasonable, and also the losses from the cylinder plays especially from an efficiency perspective, but also from a comfort, delivery and usable hot water perspective. So again, insulating all that pipework is critical. So yeah, anything else though, Tim? Happy to touch base with people, and thank you very much for all the questions. There's some really good ones in there.
Thank you, Paul. If you can click the ones that you've answered, so I don't end up duplicating them, and I would. Everybody else, by the way, can pick out any that they wish to address. Stuart, you didn't give a presentation, so I am going to direct a question towards you, and I hope
absolutely fine. Yeah,
that's okay. So there's a comment coming from William Wiltshire, which is that the trouble with servicing unvented cylinders is that when you test the valve, they rarely reseal, and you end up having to drain down and fit new, and your customer thinks that you're ripping them off as it was fine before you touched it. Any thoughts or comments in respect of that?
Well, they should be sprung loaded on the hot side and should reseat. I'm not seeing it as a common problem. Of course, the manufacturers will state they only want to warrant them for a year anyway. It's a difficult one. It's part of that annual check, of course, is see that they're functioning properly. I mean, you could argue, is there some other parameter at play? You know, is there something like especially on the hot? Is there scale involved? Is there something that's not preventing that from reseating? I can't really say a lot more than that.
Okay, no, not at all. But you took it into the area of the servicing there, which was obviously touched upon in Jerry's presentation too. So, from the manufacturer side, what would you add to the commentary around the issue of servicing and affecting the warranty of the product and indeed the product lifespan?
Well, it's twofold really. The warranty is obviously there. The servicing is there more from a safety to the consumers. Ensure it's functioning and you're in accordance with the G3 and the regulations. Obviously, as a manufacturer, we have an obligation to meet that criteria as well. The main thing which we touched on is very much about water quality and what's it being fed by, and if there's any other additives or things in the system. But generally, stainless steel is very robust to most water types, and it's very, very rare that you get a problem manifest in that time. It's usually something that's at fault very early on, so it's usually something, an additive or something that's in the water or where that water has come from. Okay.
Yeah, thank you very much. Gary, there's a question come in from Thomas Rzinski, which asks if will reducing the velocity of soft water help with the lifespan of copper pipe work?
Well, reducing what, sorry?
Will reducing the velocity of soft water help with the lifespan of copper pipe work?
I mean, the starting point is really knowing what the water is anyway in the first place. What is the pH value of that water with regards to what action you may take, really, in real terms. Taking some action towards it will help with regards to, you know, like cylinders with anodes in and things like that. I mean, from my experiences, it's one of those things, it's whereby when you come across it with copper, the biggest nightmare I ever had was some years back where I worked in this very large building, and I was quite inexperienced back then, I must admit, at the time. And I saw these two 2-inch mains running down the basement, and I saw these green speckles on the pipes. I thought, that's strange, what's that? And I rubbed my hand on it, only to find the water started pouring off. I thought, oh my God, this 2-inch copper supply, it was a big hotel, had literally gone. And that was for many years, basically, again, from a soft water area. It was in Barrow-in-Furness, actually, where it was. So there's certain areas, is what I'm saying, where the soft water is, and that's why the testing is so important to get it right at the beginning, to make sure what material you should be fitting at the end of the day. And, you know, there's so many more materials available now for pipe work, let alone copper, that can actually get over these problems anyway. So necessarily, is it going to be copper in the first place?
Yeah, I think the question is about sort of velocity as well. Will it improve it? I mean, obviously, if you increase the turbulent flow within a pipe, increase velocity, then you may get increased effect on the pipe work. But obviously, with Legionella, you don't want laminar flow. You want turbulent flow. You want higher velocities, arguably to to remove any potential for biofilm or anything like that. So it's a tricky one, but yeah.
Thank you.
Okay, thank you. Sorry, excuse me whilst I just scroll through some more. Here's one that you may not like, but I'm going to throw it out there anyway. Dave Toddhunter has said, United Utilities have put West Cumbria on borehole water. So who becomes liable for cylinder failures?
Okay. Wow. Cheers, Tim.
I think that's an open debate on how much of a warranty you want to give, isn't it?
Clearly borehole water in the manufacturer's instructions is not suitable. That's all I can say. If you read the manufacturer's instructions on the vast majority of manufacturers I've read, bore water is not suitable for copper, well, for cylinders generally. That's what it stipulates. So, you know, you'd have to go back to maybe, you know, say back to that water provider, isn't it, to sort of say, well, you know,
I'd want to see, if it was a serious project, I'd want to see some kind of test data, and then we could do the further analysis we could do is speak to the steel provider, and I suppose it's not also that, it's also the weld quality as well, that you haven't got pitting and things like that. So in the main, if I had to summarize, generally you'd write a different warranty for that specific case.
There's some good questions in here, Tim, about phase change material. Phase change might be some in there for Lucas. I don't know if you've clocked them.
I haven't got that far yet, but please read it out if you can see it, Paul.
I'm trying to find it. If you want to put a couple in, and I'll let's have a look.
Okay, so I've got one here, Lucas. On the Sunamp units, given the heat source is similar to other systems, i.e. electric/boiler system, etc., how does it manage to be more cost efficient? It's a really interesting concept.
Yeah, thanks. Yeah, so obviously I didn't have a lot of time to go through all the USPs of the product, but because we're not cylindrical in shape, we can use a different type of insulation, which is called vacuum insulation panels, and essentially they benefit from the fact that it's mainly air that will that will transfer the heat, and all our thermal stores are A+ rated and have a very, very low heat loss. So roughly about half the heat losses of an equivalent cylinder. Another thing, and obviously this comes a little bit back to the question, is it actually done, is that the product itself is essentially maintenance free. We have in all our products less than 15 liters of water, and therefore there's no requirement to fit a pressure and temperature relief device on the unit, and therefore also no requirement to service that device. And that is in particular for social housing providers and other players in the market, where the annual service is actually a requirement that is more likely to be carried out. Is a very, very strong proposition as well.
Thank you very much. And Paul, I know obviously you've been doing quite a lot of work on behalf of the CIPHE on systems and the future with low temperature heat sources. So there are a few questions that have come in around that topic. So I'll try and pick some out here. Have you any thoughts on air source heat pumps providing only around 55 to 50 degrees centigrade primary to a cylinder, leading to low storage temperatures, unless an immersion is wired in to raise the storage temperature to at least 60 degrees? You're on mute, Paul, sorry.
Usual schoolboy error, sorry. Yeah, that's true. I mean, there's a lot of heat pumps on the market. Most of the reputable heat pumps, which all of them will have a means of raising the temperature. I mean, a lot of refrigerants now, a lot of high temperature refrigerants on the market, which will negate it, but there will always be products that find their way onto the market that are a maximum of 55, which will require an immersion heater clearly to maintain that temperature, and which obviously then uses a higher carbon intense fuel, being direct electric rather than the air source itself. So and the more insulated the property, the more we've now got the domestic hot water, which becomes the highest basically load in the building. The heat load is that small, it then becomes the highest load. So it then, as a property, looking at it itself, the actual carbon emissions from that then becomes quite high. So it's a really, really good question from one of the audience, Tim.
So, I mean, I think I'd say, Paul, though, on that is your temperature, your delta T you've got to raise at the end is so small that recovery, if you had it on a cycle periodically every 24 hours, the actual consumption annually isn't a great deal. I appreciate your initial load could be.
Well, we need to get that temperature between 60 and 65. And I mean, the other thing to bear in mind here as well, Stuart, and again, this is, you know, we're not saying, you know, it's doom and gloom, it's all over, you know, we're clearly not saying that. But, you know, you should be maintaining a minimum amount of energy in that tank. You don't want it dropping probably below 50, 45, 50. You've always got a little bit of energy in there for washing up, for stuff like that. So you really need to get it above those temperatures to make it usable. But I mean, external plate heat exchangers and charging systems is, I personally would, if I'm, you know, again, I used to install systems, I would be looking, and I don't want to get shot down for this, but I'd like to install external plate heat exchangers so I know I'm getting the maximum power into that cylinder. There's no degradation of that coil in the cylinder, and I've got nothing against coils in cylinders because, again, they're absolutely fine. But me personally, not the CIPHE, I would fit external plates or a charging system, so I know I've got more usable energy in that tank, as well as when I come to reheat, I'm actually getting the full maximum power into there. But yeah,
it's a very good point.
Thank you both. Unbelievably, there are even a couple of questions that come in that I can answer, which is just a couple of questions about incidents of Legionella, and I have posted a link into the chat which will direct people to the Legionnaire's disease monthly surveillance report for England and Wales that is maintained by the government. Those are the clue is in the title. Those are supposed to be monthly. Actually, the most recent report submitted was or published rather ran until the end of October 2020, and I think there's been something else going on which may have otherwise occupied them from staying up to date with their Legionella surveillance reporting. But that is the link via which you can keep an eye. CIPHE certainly uses it for monitoring and indeed reporting and comparing incidents of Legionnaire's disease, comparing the changes year on year. So that's in there for people who are interested. We'll get back to the real technical people who are on this call.
Tim,
yes.
just pointing out as well, one of the things we haven't mentioned is priority hot water. Obviously really important.
Go for it.
Well, just it's that, you know, priority hot water, meaning that we have a single feed. The whole output of the system going into the cylinder is critical as well, especially with lower temperatures. Albeit when we get into the peak cold time of the year, there has to be some thought about, you know, let's say we size, let's say we have a 6 kilowatt heat load, and we prioritise that for a hot water cylinder at high usage at the coldest time of the year, are we going to starve the heat from the property? So the difficulty is you'll find that the hot water loads predominantly will be higher, again, dependent on the hot water usage. So it's important to have that priority hot water as well.
Okay, thank you.
And I'll give a question to Lucas, actually, if you don't mind, Tim. Lucas and Sam. Obviously, your units, I've seen them before, Lucas. I've done a lot of research on PCM. I think as we move towards, if we can reach those difficult targets, and they're difficult targets of potentially 600,000 heat pumps per year in 2028, which is, again, government are really focusing on, which is a third, probably more than a third of the current annual boiler sales. Technology such as thermal batteries are critical in that transition, because, you know, if you are looking, if your options today is, you know, you've got a combi boiler and you decide as a consumer you want a heat pump, you now have to fit a cylinder. You've got to find space for that cylinder. I know you've got to find space for the heater. So actually, out in the field, I know there's potential things that they need to be aware of with such technology such as yours, such as the critical elements, making sure that they're able to deliver enough head of pressure to your heat exchanger. Do you want to touch on that, Lucas?
Yeah, sure. I mean, so in terms of installations with heat pumps, obviously it is important to maintain the minimum flow rate for the heat pump. And in our manuals and in our literature, we have all the pressure drop characteristics of our product. Currently, the current generation still has a fairly high pressure drop compared to standard cylinders on the primary side. But we currently have a new generation of heat exchangers in preparation that will significantly reduce that, and it will be in range with standard heat pump cylinders. And yeah, I mean, obviously, I think it is really important that installers also look at the pressure drop across the secondary side as well. We do recommend that our products are fitted or should have at least 1.5 bars of pressure at the inlet to deliver you know, a sufficient pressure at the outlet, at all the outlets. But really, it is a case-by-case decision. They are rated for up to 10 bars of operating pressure. So you know.
Yeah. So in your unit, for example, the one that would be fitted to a heat pump, you have two heat exchangers in there. One is the primary from the heat source, and then you've got your domestic hot water coil, so it's instantaneous hot water, isn't it?
Yes. So it's essentially the same heat exchanger. It's one block, but it's got two different coils inside it.
Yeah.
And one is obviously the primary coil, and the other is the secondary coil. Yeah. And as you said, we never store water for long. Because essentially, as I said, our largest unit has less than 15 liters across both coils. So in total, it's less than 10 liters on each individual coil, and that means that even with, you know, washing your hands twice or something like that, you will have replenished the water and completely exchanged the water inside. And then obviously once you start factoring in showers, etc., the water gets replaced several times over.
It's disruptive technology, isn't it, basically, at the moment?
Yeah,
it's
absolutely.
The hot water storage market very slowly.
Slowly but surely.
No, obviously cylinders will always be there, but what I like about phase change materials is you can have all shapes and sizes that can fit everywhere, and I think that's where innovation is going to play a critical role for installers to make their life easy. Is you know, all the different shapes that can fit in areas where a normal cylinder couldn't, so plays a big role as well.
Yeah, so we have examples of installations where they are, for example, in the void underneath staircase, But there's also other options, looking at void spaces behind walls, for example.
Thank you both. Stuart, I'm going to direct another question or two in your direction as well.
Okay.
I'm pretty sure that Jerry will be able to contribute too. I've got a question which says, do you need to run 22mm from an unvented cylinder as it is on mains? No manufacturer seems to have any mention on the pipework leaving the boiler. 15mm loses less heat, especially to basins.
Yeah, I mean, as a bare minimum, we're bringing in 22mm to guarantee a good flow rate, more than anything, without a high pressure drop, and that's your restriction. With the whole point really of having a cylinder is that you've got a good flow rate for multiple outlets. If you were talking, say, a combi boiler, then yeah, the restriction is the load that the boiler can deliver. But the whole point of having a vessel is that you have a high flow rate. I don't want to mention a competitor's name, but there was a reason why it was given something like a high flow designation, and it was really for that reason.
And as I say, so I agree. It's most people tend to put 22 on the outlet, at least the first branch, and thereafter. But it does depend on the load at the end of the day, because how many bathrooms or whatever you've got on the other end of that pipe ultimately, that you're calculating litres per minute to supply at the end of the pipe ultimately.
Or it could be a worst case scenario, couldn't it?
Yeah.
It goes down to loading units, Tim, and that's not one for here. You know, loading units calculation, simultaneous demand. What is that simultaneous demand going to be from the outlets? You know, there's the BS, or was it EN 806, which will give you a method of calculating. But generally, you know, if you're in a domestic property that looks like it's going to have a high demand, then you would have to calculate accordingly. And that's where the amount of 22mm will differ to what it would normally, because again, you generally don't want more than you need a bar. Some of the outlets will require a minimum of a bar dynamic pressure, so you want to make sure that you get that at the outlets, and depending on how many you require in one go will depict what pipe size you have.
We're also seeing a shift a lot more in high spec domestic to 28, where you've got these high showers, which I appreciate is deviating a little bit from the low carbon angle. It is just a market force that's present.
Yeah, but the Legionella police will jump all over that one, because they'll say, what's the potential of laminar flow? So we have this, you've always got this balance between.
You've got a trade-off, haven't you? You've got to have an understanding of the system.
I mean, we did a lot of research with CIPHE on the loading unit normalisation. You know, pipework is apparently being oversized, especially in multi-residential properties, so which leads to laminar flow, which leads to potential biofilm and issues. So we are allegedly oversizing anyway. So it's a difficult balance. It really is.
Okay, I'm mindful of the time, and I promised everybody that we will finish by 7:15. So we're into the last 5 minutes. So just to repeat what I said earlier, any outstanding questions we will collate and to respond to when we share the video as well. I'll just fire out a couple of quick ones that strike me. Are those heat batteries generating any noise?
No, they're not, apart from a small relay that's inside.
Okay, and what size electricity supply is required to operate the SunAmp unit?
16 amp supply, because it has a 2.8 kilowatt element inside. So generally whenever there was a cylinder in place before, that supply is suitable.
And I can't find it here, so I'm recalling off the top of my head, but somebody was asking it about if you have any price comparison charts.
I don't have price comparison charts here, but we are price competitive with market-leading cylinder brands.
Okay, is there any cost comparisons? I think that addresses the same. Okay, I'm trying my best here to grab, so if anybody else sees anything, then do feel free. But there was a question about how long does it take for Legionella to proliferate in a hot water system for a given temperature?
Wow. So do you want me to answer that, Tim?
If you can, yes, please.
Yeah, so on my slides, again, I was just touching on the different temperature ranges. So, for example, 60 degrees is said to be destroyed after 2 minutes exposure. Over 60, over 50, between 50 and 60. Legionella bacteria is still active but dying off. So 19 minutes exposure at 55 degrees, and that's within the CIPHE Safe Water Guide and Legionella Risk Assessment Guide.
Okay, and just on a different angle, because you mentioned it earlier on the subject of priority hot water, would you look to have a buffer to help the heating side?
What for? So again, would I have a buffer personally? It would help, obviously, because it'll help with response time for when the unit fires up or if the heat pump is running. So you're going to get instant temperature. It will add to the amount of energy available to the actual overall system because you're storing more energy. But to be honest with you, it depends on the property, depends on the application. But I wouldn't, especially if I have a cylinder with an external plate heat exchanger. As long as my cylinder's sized suitably, I would be happy with that.
Okay. Somebody else I saw and can no longer see because of the rate that the questions have come in. Somebody asked about the low temperature heating course that was referenced, and that is just a thing that is in development at the moment and is expected to be available within the next couple of months, certainly. And the CIPHE will be communicating widely about that availability. So we will make it very difficult for you to miss when that is available, let me assure you.
I mean, the key thing to point out here is, Tim, we're involved with MHCLG, the Ministry for Housing, and design has always been there as a responsibility of installers, as a competency, as a minimum competence. But it's mainly, if you're looking at new build, an installer would install to a design. So as that competent personcy scheme, it's at the business. But there's a big debate now about design needs to be, bear in mind that 90% of installers, apparently one-man bands, installing in houses, they should have that minimum design experience. And we're not going to turn people in designers overnight. The key thing about this training course, Tim, is, everyone's busy. We've got let's say a 2-day course. We're not going to turn people into designers overnight, but obviously we can give them the relevant skills and the basics to then go out there and implement things correctly. So the course has been developed in a way that hopefully makes it easier for the installer to understand. We're not going to sit there with a calculator. We're not going to sit there doing all sorts of formulas and exposing formulas. It's, you can pick up design books and just get engrossed in it. And I mean, I'm going to go back to when I was on the tools, Tim. I remember I picked up the Domestic Heating Design Guide about 20 odd years ago, and I tried to carry out heat loss from the book. And, the challenging thing is, am I going to do that in every job? Did I win the job? No, I didn't. So you're supposed to carry out heat loss. But again, it's, go back to the Mears calculator that was effective. And there's a lot of digital tools now to help installers to carry out these design exercises on the move. But I think it's critical that you understand the basics behind it. Otherwise, it just becomes a black box and we're at risk of garbage in, garbage out. So the training course is the basics, Tim. It's not going to turn them into a designer overnight, but it's critical to get the basics.
I have one question that I really want to get across, because I think it's it's somebody who needs some assistance, and it's something that we can follow up on. But Leicester City Council have been handed £25 million of SALEX funding. I have an army of project managers wanting to install air source heat pumps in schools and other commercial buildings to heat water and existing heating systems. I'm concerned about the low temperature output from the air source. What would you recommend from a design perspective meet the heating and hot water needs? First of all, does that person need to be concerned about the low temperature output from the air source?
I mean, it depends on the product. I don't, again, you know, I know a lot of the manufacturers that they will go up to 65, 70 degrees with the change in refrigerants. So again, it's a case by case, but happy to touch on that one anyway, Tim.
Okay.
Afterwards, but again, it's not something we can answer, but it's something we could potentially have a chat about.
Yeah. Well, we will be sending out some information following on from this evening's session. So the opportunity for following up with us will be there for person who asked that question, and indeed for anybody else. So please do take it. I'd like to thank everybody for joining us this evening. We couldn't even get through a quarter of the questions, so apologies if we haven't reached yours. And as I said, we will arrange for a response to those that have come in. And I'd really like to thank Lucas from Sunamp and Stuart from Fabdeck for their time this evening. Very much appreciated. And of course, from all of us at the CIPHE, thank you once again.
Thank you, everyone.
Thank you.
Thanks.
Have a good evening.
Thanks, Tim, for having us.
Thank you.
Thank you, everybody. You're very welcome.